Here's some more examples of using integration by parts to integrate a product of functions. So let's recall the formula for integration by parts. It is the integral of u dv is equal to u times v minus the integral of v du. So we need to pick u, and we need to pick dv in our original problem. And remember, u is chosen so that its derivative is simpler than what we started with. So I'm going to choose x to be u, and that means that dv is then ln of x dx. Okay, so in our formula we need u and du, so I'm going to take my u that I have here and find the derivative of each side, or the differential of each side. So du is equal to dx. And then in my formula I also need v, but I have dv, so that means I need to integrate both sides. So the integral of dv is v, and then I need to find the integral of ln of x dx, which we don't have a formula for that. So that means that choice won't work. Okay. Well, that's okay. That happens sometimes. So what we do is we start over. We choose a different function for u and the different function for dv. So if I chose u to be x and it didn't work, then that means I'm going to try ln of x to be my u. Now, when I take the derivative of that, it will be something simpler than what I started with, right? The derivative of ln of x is 1 over x. And so then dv is going to be x dx. Right? X dx. And ln of x was my u. Okay? All right, so we said the differential of u is going to be du, and then the derivative of ln of x is 1 over x dx. Okay, so that part's done. We got my du. And then again, we're going to integrate both sides of the dv equals x dx. So we get v is equal to the integral of x dx, and the integral of x is 1/2 x squared. Okay, that's much better. So let's plug that into our formula here. So u dv is equal to u times v minus integral of v du. All right, so u was chosen to be, in the one that worked, ln of x, times v, and v is 1/2 x squared, so I'm going to put that out front there. Okay, and then minus the integral of v, which is 1/2 x squared, and du, where's du? Du is right here. And that's 1 over x dx, so times 1 over x dx. And we notice that x squared over x is going to be just x. So this actually simplifies to 1/2 x squared ln of x minus the integral of 1/2 x dx. So quick integration there. We got a 1/2 x squared ln of x minus 1/2 integral of x is 1/2 x squared. So I end up with 1/2 x squared ln of x minus 1/4 x squared plus c. And of course, you should check to make sure that the derivative of that gives us x ln of x. Let's move on to our next example. Okay, there's that integral of ln of x that we had in the last problem that didn't work out for our integration by parts. So it turns out we can find the integral of ln of x, but we need integration of parts. So that previous problem could have been done, but we would have had to do another integration by parts within it. And it turns out just switching our u and dv worked better. So let's see how this works out. So again, as we learned from the last one, that if we have an ln of x, that might be our best choice for u. So let's try that. And that means that dv is going to be whatever's left over, which is dx. Okay. So then we differentiate u. So we get the differential du, and the derivative of ln of x is 1 over x, the derivative of the argument over the argument, dx. Okay, and then dv, we need to get v, so we integrate both sides. Well, integrating dv gets us v, integrating dx gets us x. So we use that in our formula, that the integral of u dv is u times v minus the integral of v du. Okay, u times v. So that's ln of x times x. So I'll write that as x ln of x minus the integral of v, which is x, times du. du is 1 over x dx. And that simplifies to 1, right? X times 1 over x, or x over x, is 1. So this is x ln of x minus the integral of 1 dx. So that's x ln of x minus integral of 1, or the integral of dx, is just x. And then, of course, plus our constant of integration. And again, you should check that the derivative of that should give us ln of x. Okay. All right, let's go on to our next one. All right, here's an example where we have a definite integral where integration by parts would be necessary. So let's take a look at that. So again, remember the definite integral is first we find the indefinite integral and then plug in our limits of integration. So here's we have an x and an e to the 3x. So we found that with those, the x, or the polynomial term, works as our u, and then the exponential term works as our dv. So if u is x, dv is e to the 3x dx, and we go to about finding du. We differentiate both sides, we get du equals dx, and then for dv we integrate both sides. Integrating dv gets us v, and then we want to integrate e to the 3x dx. And remember our formula for e to the constant times x is 1 over the constant, e to the constant times x, and we have what we need now. So u dv, the integral of u dv, is u times v minus the integral of v du. So we chose our original problem as u and dv, so it gives us u times v, so that's x times 1/3 e to the 3x, so that's 1/3 x e to the 3x minus the integral of v, which is 1/3 e to the 3x times du, and du is dx. So 1/3 x e to the 3x minus 1/3 the integral of e to the 3x, which we already integrated, we know is 1/3 e to the 3x, plus c, and we'll clean that up just a smidge, 1/3 x e to the 3x minus 1/9 e to the 3x, plus c. But remember, original problem had limits of integration, right? So we could go ahead and plug those in. So we have from 0 to 1. So I'm going to do that up at the top of the page. So plugging in 1, I get 1/3 times 1 times e to the 3 times 1. So that's 1/3 e cubed minus 1/9 e to the 3 times 1. So that's e cubed. And then when I plug in 0, I get 1/3 times 0, which is 0, minus 1/9 e to the 0. So this is e, we'll factor out an e cubed, 1/3 minus 1/9, and this is going to be negative 1/9, right? E to the 0 is 1. So this integral is going to be equal to e cubed times 1/3 minus 1/9 minus a negative 1/9. And you can plug that into your calculator if you want to get an approximation for that and figure out what that might be. Okay, one more. Now this is x squared times e to the x, and it's also a definite integral, so we'll have to keep that in mind. But this is, again, a good candidate for integration by parts because u substitution won't work here, because normally if we have u substitution, you want to pick something that its derivative is present also in the problem, but it's a little tricky here. It's not going to work out. We're not going to get a simpler or easier to integrate problem. So we're going to go ahead with our u substitution, or integration by parts. U substitution won't work. So again, when I have polynomial and exponential, the polynomial is usually the best choice for your u, and the exponential is a good choice for your dv. Oops, that should be a dx. There we go. Okay, and then derivative of u, or the differential, is going to be, here's 2x dx, so no, slightly different than what we've been getting before. And then the integral of dv is v. Integral of e to the x is just e to the x. So when I plug that into u dv, the integral of u dv equals uv minus integral of v du, we get u times v, so that's x squared times e to the x minus the integral of v du. So du is 2x, so I end up with 2x e to the x dx. Okay. Now notice I have an integral that now I will need to do integration by parts again. Right? This here is an integration by parts problem. So I'm going to go ahead and do that again. So this time I'm going to pick u to be 2x and dv to be e to the x dx. Okay, the differential for u, du, and here derivative of 2x is 2, and the differential is dx. And then integrating dv, we get v. Integrating e to the x, we get e to the x. So that gets us, let's see, x squared e to the x minus the integral of 2x e to the x dx is equal to x squared e to the x minus, now we're going to use our formula, our u v minus the integral of v du again on this function here, on that integral there. So let's see, u times v, so that's 2x e to the x minus the integral of v e to the x du, so that's a 2 times e to the x dx. So that's going to be x squared e to the x minus 2x e to the x. So now I'm distributing the subtraction, and plus the integral of 2 e to the x dx, right? So I'm subtracting the entire quantity represented by the integral 2x e to the x. And using integration by parts, we get two parts to it, that part, and I need to subtract both parts. So that's why this one becomes positive there, that term. And so we just have one more integration to do. And that integral is 2 times the antiderivative of e to the x, which is e to the x. And just like the last one, we have to remember to use our limits of integration, right, from 0 to 2. Okay, and I'll leave that for you to plug and chug on that one. Plug in 2, figure out what you get. Plug in 0, figure out what you get, and then subtract. Okay? All right, that's it.